Today we will take the first steps on the road to understanding a process that is often difficult and sometimes disheartening. Today we hope to shed some light on upsetting. Pushing material back on itself is one of the fundamental processes of forging, and it is notoriously the most difficult, both in the power and balance that is required to produce a consistent and desirable result. It is in this most cruel of circumstances that you can see the advantages of using a machine to forge over that of hand forging, unto the point that oftentimes the differences are mystifying, yet the principles are the same, and only with a working knowledge of the blended processes can you direct it no matter how much power and control you have. Today we will be using two machines to help shed some light on some of the basics of upsetting. First, we will use a dynamic pressure hydraulic press that can apply upwards of 35 tons of pressure and moves quickly, for a press, at speeds upwards of 1 meter per second. This rigid framed press has many advantages, not the least of which is its ability to keep the press head and table in line with one another, even through significant side loading. Nevertheless, it is not the perfect upsetting tool. The press has its advantages and disadvantages. As the press head hits the workpiece, the ends are pushed towards the middle. The ends do not flow away as quickly at the center because they are in traction with the head and the table of the press. Oftentimes, smiths will refer to a hammer's blow being a soaking blow, and in that they mean that the force from the hammer's blow penetrated deep into the steel due to a high head velocity and long detention time. The result is a swelling of the bar being upset further away from the head of the hammer rather than the top flaring right next to it. The principles at work behind this observation are simple to explain when looking at the reaction of the metal closely under the press. The center of this bar has the least resistance to flow, and thus once this cylindrical structure is put under load, the center will flow fastest as it increases in size. The end will only then trail behind in the amount that is deformed. Quickly, however, in this case, the piece is pushed flat and the surface area of the ever-cooling steel in contact with the press head and table increases until it covers an inch-sized dot. The pressure of the press reaches equilibrium with the structure of the steel, and we have done all we can do to this piece of work. What has happened here is not that much different from what happens with a hammer when you get that soaking blow, but it is important to note that it is a characteristic of the flow of the metal, not some magical property imbued by the hammer. As we increase the height of the metal, the area able to swell in the center is also taller, and the chance of losing balance becomes greater. This is first apparent in how the end of the bar drifts off-center, and finally in the bar folding over on itself. Now to the hammer. The power hammer we are using today is a Big Blue 155 with large flat dies. This hammer is set at full air pressure and in the downstroke can achieve speeds approaching 27 meters per second or around 60 miles per hour. This high speed is the hammer's way of generating pressure as the head decelerates, and while that pressure can exceed 150 tons for a nanosecond or two, it takes multiple hits to do the same work as the press, and that's where instability can creep in. But the end pressure of even a small power hammer exceeds that of a press many times its size. So is a press the best way to upset? No, not at all. The two are simply different. It is here we must point out that while the press may do a better job of providing a deep soaking blow as it upsets the metal, the power hammer, and even more so the hand hammer as we will explore in a later video, can take advantage of the material's inertia. This is the workpiece's resistance to accelerate in a different direction, or in any direction at all, something the press with its relatively low speed cannot do. This is referred to sometimes as slapping the metal. As you can see here, that doesn't help but so much to keep your upset on center once you lose your balance on a tall piece. This characteristic can be taken advantage of to greater effect in many of the upsetting techniques we have come to think of in blacksmithing. These two subtly different ways of delivering energy into your workpiece lay the groundwork for understanding upsetting and why the metal you are working on is doing what it is when you hit it. Oh, and it's fun to smash stuff too. Thanks, and subscribe to keep up with what is new with Blue.